Hello everyone and welcome to today's webinar on SEM Cathodoluminescence. My name is Vivian Ho, Marketing at Eurofins EAG Laboratories. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Udit Sharma, Project Manager, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our first presenter, Mike Salmon, Scientific Fellow, Advanced Imaging Group from Eurofins EAG Laboratories.
Thanks, Vivian. Once again, let's see here. Let's see, I can make sure I can advance everything. Perfect. Well, welcome everybody. Once again, my name is Michael Salmon. I'm a Scientific Fellow for Advanced Imaging Group here at EAG. I'm based out of the lab in Raleigh, North Carolina. My background is in material science and engineering, where I received my PhD at NC State University with an emphasis on microscopy and surface analysis. And I've had an almost 15-year career now at EAG focused on highly localized characterization and failure analysis, primarily of compound semiconductors. And so today's webinar, just a little brief outline here for you. Give a brief introduction about Eurofins EAG Laboratories. We'll go over the somewhat famous SMART chart. We'll talk a little bit about cathodoluminescence principles, the instrumentation available at EAG for cathodoluminescence. We'll go over a few application examples and then look at a case study of a commercial high brightness LED, just trying to explore some different ways we can visualize and analyze CL data, and then a quick summary. So a little bit about Eurofins EAG Laboratories. We're a network of independent labs with over 600 highly educated employees at 20 plus locations worldwide, and we serve approximately 4,000 plus clients in 50 different countries around the world. So for essentially almost any kind of analytical technique you can think of, we probably have it. So if you have any kind of questions regarding that, feel free to ask us anytime, email us, etc. And so with that, we'll get to the SMART chart. So let's take a look at this. The SMART chart is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool, SMART, and it shows the techniques we have available at EAG plotted to show their different attributes related to spot size down here and detection limits. All right, either here in atoms per centimeter cubed or atomic percent on the right. And let's see, so within the box, you can select your technique based on the detection limit you need and the size of your area of interest. Outside the box are techniques that don't quite belong in the chart. Techniques on the right, for example, don't necessarily have a spot size associated with them, so they're considered a bulk technique, and they may consume your entire sample, for instance, but they have, in some cases, very incredible detection limits, such as GDMS or ICP-OES, etc. And then the techniques at the bottom here are basically imaging techniques that don't provide compositions, but they do have some relevance with regards to spot size. So that's why they're placed down here below. And so today we're talking about SEM-CL, which covers this sort of range within our chart. So we've got analytical spot sizes. We can analyze structures from, in the micron down to tens of nanometer kind of scale. And then we have sensitivities, 1E16, 1E17. So some capabilities for looking at dopant level compositions as well. So what is cathodoluminescence? Cathodoluminescence is essentially light that's emitted by the sample after irradiation by electron bombardment. And so in our case, we're going to use a scanning electron microscope to provide the primary electron beam, and this is going to be in some kiloelectron volt range, so like 1 kV to 10 or 30 kV, for instance. And then that interaction with the electron with the sample then creates a variety of different analytical signals that we can analyze. Very familiar with SEM, secondary electron detector. Secondary electrons have energies ranging from about 1 to 100 eV, and they primarily carry information about the sample composition and topography mostly. And then we can also collect things like backscattered electrons, which are typically keV range. We can look at X-rays, which are a much higher energy as well, kiloelectron volts. And then in the case of cathodoluminescence, now we're talking about photons that are carrying information in the EV range. And so with our instruments, the typical emission, CL emission we collect is from the UV, about 200 nanometers up to near infrared, about 1700 nanometers. And so with this, we can understand quite a bit about the different samples that we can look at. So what creates and modifies the CL signal itself? So in semiconductors, if it's bombarded by electrons with sufficient energy, electrons from the lower valence band are promoted into the higher conduction band here, right? And so then we have a few different situations here. We've got some different intraband trap states denoted by these lines here within the band gap. And so we have a couple different situations that can occur. You can have electrons that then fall back down to the valence band, recombining, and this generally emits the energy of the band gap of the material. You can have a situation where you're interacting with a single trap and it falls back, so now you've got a little lower energy, so a little bit longer wavelength of light is emitted here in case 2. And then in case 3, you have multiple interactions that occur, so then you have further redshifted information. So generally the intensity of the CL signal, the light we're collecting, is a function of the density of the trap states, and then the wavelength of the CL signal is generally a function of the type or the interactions here, 1, 2, or 3, et cetera, that we're having within the band gap. And so what can we learn from the spectra themselves? What are the different spectral analysis parameters that we have access to? So the 3 main ones are intensity, so we can see how bright the emission is, for instance, and then secondly, the wavelength, so what energy or wavelength the light is being emitted at, and then thirdly, the full width half max, so the sharpness of the emission. And so from these different aspects of the spectra, we can understand different aspects of the sample, from composition, strain, defect densities, doping concentrations, etc. Then it's important to note that the spectral resolution is governed both by the instrument, so we can change gratings or change the settings of our instrument to effectively change, let's say, things like the dispersion of the light across the detector, as well as the sample itself. And that's both the material and then also temperature dependence of the sample. So these are all parameters we can investigate with these kinds of analysis if you have the right type of tool. And some of the things we have to think about with regards to SEM-CL are what is limiting the spatial resolution, or what kind of resolutions can we achieve with this this technique. And primarily the resolution is going to be limited by 3 basic parameters. The first is the probe size, so the spot size of the instrument. Typically this is going to be on the order of a nanometer or so fairly small here. The generation volume, so as the electrons impinge on the sample and then go through scattering events within the sample, this creates what's known as the interaction volume or generation volume within the sample. And this is dependent on the accelerating voltage of the primary beam and also the material that you're shooting the electrons into. This tends to be on the order of tens of nanometers to microns, depending on what you're looking at. And then lastly, we have the diffusion length. So essentially how long are carriers able to exist separated within the material, how far they can diffuse before recombining and giving off light again. And so this is a very material as well as geometry dependent parameter, and in some cases can be as low as about 15 nanometers. So what we'll see is that typically diffusion length and the generation volume are going to be the main ones that limit our resolution. We're going to be working with SEMs that have much smaller spot sizes initially, so that's really not going to factor in too much. And one thing to think about here is that essentially cathodoluminescence actually gives us the ability to detect atomic size structures and defects. Even though our probe and our interaction volume is much bigger, we're able to excite these kinds of smaller defects. For instance, here we can look and we can indirectly see the effect of threading dislocations in gallium nitride. So each of these individual threading dislocations acts as a non-radiative recombination center. So we're effectively mapping out the diffusion length within the material, and where you have a core, dislocation core here, you're getting carriers recombining without giving off light. And so we're able to detect this atomic scale structure with a much larger overall probe size. And then there's another secondary example here is looking at quantum dots along a gallium arsenide gas nanorod, for instance. And so here you can see the specific emission here around 650 of the quantum dots along this particular nanorod. This one has a lower concentration, and here's the gas core. So we can separate out, we can see these very small 20 nanometer or so quantum dots, although it's much smaller than our effective probe size. And ultimately, this concept, this is great. So we have really good detectability for very small structure, but on the other hand, you also have to take that into account when you're thinking about convolution of information or convolution of spectra ultimately. And so we'll talk a little bit about that, and then at the end of the talk, we'll talk about how other potential ways to get around that or improve on that, potentially by going to TEM-based techniques. So here at EAG, we're somewhat blessed to have an Adelaide SEM Cathodoluminescence system. And this system comprises of a SEM, an electron gun here, a variety of vacuum pumps and a vacuum chamber, coupled with a spectrometer here off to the side. And the beauty of this instrument is a custom-made SEM column with integrated light collection optics. And so this is kind of unlike any other CL system available currently. This really allows for optimization of the technique and is really designed to be truly a SEM-CL instrument. So, and then lastly, we have a low temperature cryostat, so we can very accurately control the temperature of our sample during the analysis, so we can understand something about the dynamics of what's going on and the light generation within our sample relative to temperature. So just to go over this system quickly, so this system, the Adelaide system, has a Schottky FEG. This provides very high brightness and good energy of resolution. We have high current densities ranging from 30 picoamps to up to 300 nanoamps. This allows for lower beam dosages on certain sensitive samples, reducing damage, and then fairly small spot size, 2 to 3 nanometers at 5 kV. And then this integrated optics portion is really important here because it really improves it gives us really high collection efficiency. So we have the best chance of collecting all the light that's being emitted by the sample. So, and then not only are we able to collect all that light, but we can collect that light over very large areas in a very uniform way. So in this case, this is an example showing the Adelaide field of view, where we get very good stable emission over a 300 micron diameter area relative to a standard side entry CL system that you may be more familiar with or you've seen. And I've had experience with this kind of system for the past, I don't know, 10 years or so as well. And this is definitely an accurate representation of what's going on. We really have a nice large area that we can analyze that has very good uniformity and reproducibility. And then lastly, we have cryo capabilities, so liquid helium cryo capabilities down to 10K. So we can, and then combine that with a basically a temperature system. We can then control that temperature from 10K up to room temperature very carefully, and do these very dedicated temperature studies, which is really important for studying certain types of behaviors within the samples. And so with the Adelaide system, we also collect data in a somewhat different way, but we collect hyper maps or hyper cubes of data. So along with the secondary electron image, so at each pixel here, we're collecting the secondary electron signal, but additionally, we're collecting an entire spectrum at each pixel. So this gives us a secondary electron image, then with a panchromatic image, so all the light intensity changing map, and then each emission spectrum is recorded at each pixel, and we can change the wavelengths based on the grading we use, etc. And then this gives us a data set where then we can do post-processing, or we can do essentially digital notch filtering, right? So here we can take this hypercube of data, we can define this map being 354 nanometers to 356 nanometers here, and then look at the intensity variance across the whole area. We can then also set up green being 359 to 364, and then this red map showing 365 to 375. So then effectively we can see where on our sample these different emissions actually arise from. And we'll go into a little more about how we can utilize this kind of strategy a little bit later in the talk. So the next thing we need to talk a little bit about is sample preparation and what's necessary, what kind of sample requirements there are. So in general, any luminescent material can be analyzed by SEM-CL as long as it's vacuum compatible. And typically we can look at epi type growth and plan view, for instance. Just cleave a piece of wafer and introduce it into the system and analyze it. We can also look at cleave cross sections. We can also use broad beam argon ion milling to improve, let's say there's cleave damage or things like that. We can also use gallium or plasma fib to prepare targeted plan views and or cross sections. And in general though, cleaving is the preferred method for cross sectioning, as there are some changes to emission properties due to ion beam damages and implants. So this is a known issue with gallium fib, but we've done a lot of work here in the lab to minimize the effects of gallium fib on our samples through different special preparation conditions. And a lot of this information really is coming from being really good at making very, very thin samples for aberration corrected STEM. So in that case, we had to learn how to make samples very damage free so we could take high quality STEM data. And so we've been able to apply a lot of that know-how to our SEM-CL work as well. And in some cases, we have to add thin surface sputter coatings for more non-conductive samples. Sometimes looking at things like on sapphire or glasses, etc. So we can add carbon layers or even very thin metal layers that don't really show up in the spectrum. And so for the Adelaide tool itself, sample size is somewhat limited. So we're limited to about a 2.5 centimeter diameter sample and sample heights of less than 3 millimeters. And so there's a lot of different things we can do to get the samples to be compliant, from mechanical prep, etc., or cleaving or whatnot. So, but just a reminder, if we end up doing any work, those are the kind of limitations. So some of the application areas, is a large range of different applications, from electronics and optoelectronics to photovoltaics, to nanoparticles, light emitting diodes, polymers, and in some cases even biological samples. And so just a lot of different possibilities. If it's luminescent, we can potentially look at it and learn learn something from it. So from all these different application areas, the things we're mostly going to be looking at are things like defect detection and characterization. This includes threading dislocations, stacking faults in materials, different inclusions, potentially also strain mapping. We can look at composition metrology, so alloy composition fluctuations, and then also some doping metrology, failure analysis situations, so looking at different power devices or different optoelectronics and how maybe degradation mechanisms in those types of devices. And then lastly, nanostructural characterization of nanowires, nanoparticle semiconductors, so finite sized, low dimensional semiconductors. So we'll just go over a few examples of this kind of analysis. So something you may have already encountered, this has become a fairly common practice, is to look at GaN dislocation densities using CL. This is just room temperature monochromatic CL at 365, so the band edge of gallium nitride here. This is a fast and considered non-destructive way of counting. And you can count up to about 5e to the 9 defect density, much higher than that. Then all these individual threading dislocations start to overlap too much, and it becomes very difficult to separate them enough to get accurate numbers. But the thing is I'm not mentioning here as well is that we can, since we have that very large field of view, 300 microns by 300 microns, we can effectively look at defect counting, defect densities down in the 1E5 kind of range. So we can actually go after a lot lower defect densities than a lot of other techniques. So in cases where the defect density is higher than 5E9, then maybe something like ECCI, which is a SEM-based diffraction technique, that's kind of useful. But as you go, and also TEM-based techniques are really good, but as you get to much lower defect densities, it becomes a problem. So you can do things like etching and imaging in SEM, for instance, or we can try SEM-CL, and in some cases it's very effective. So secondly, this is an example of looking at silicon carbide substrates. So in the SEM, there's not a whole lot going on. It seems fairly smooth and flat. And in this case, the hyperspectral image shows quite a few different things going on. So this is an average spectrum from this region. And so then we can do this notch filtering again with blue, green, and red. And here the blue band is denoting point defects. So this is the emission coming from different point defects in the substrate, and the green band shows us where the 3C silicon carbide inclusions are. You can see a little bit essence of here and a little bit over here more. Seems like mostly the red band is dominating. You can see how intense it is, and this is basal plane dislocations that are occurring here. We see evidence of that. Dark lines show us where stacking faults are in the material, and then there's very few points here. This is a fairly large 120 by 120 micron map, and you can see there's one threading dislocation that we see here. And so this is a great way to very quickly assess substrates, for instance, and get an idea of these different defect type densities across the surface. So getting into looking at alloy composition metrology, this is an example of showing SEM-CL of it's a GaN on silicon structure with a variety of AlGaN buffer layers. And so from extracting spectra from each of these points here, we can see we have very different band edge emissions, and then we can correlate these peak energies to the aluminum composition. And this is looked at and compared with XRD data, and we find that there's very good agreement between the two. And so we have an effective way we can actually calculate or quantify the composition of the AlGaN in very thin, small regions, right, that may be very difficult to do otherwise. And so then that leads us into looking at some minority composition, so dopant composition metrology. This is a similar sample where we're actually looking at here's the gate foot underneath this is a GaN hemp structure. So here's the gate foot here, and here there's an aluminum nitride. Thin aluminum nitride layer, we see these forms of a V pit structure here. So we pretty clear there's some sort of extended defect that's propagating through the epitaxy. This is SEM again, and so then this is our CL map with a variety of notch filters placed on it with different colors, so we can see the different compositions of the algan layers. We can see there's different emission that comes from the carbon compensated GaN layers here, as well as the unintentionally doped surface layer. And what we can see very clearly is that around this extended defect, we get emission that's more like the unintentionally doped layer at the surface versus the carbon compensated layer. And so if we then look at just the mono CL for the 360 emission, you can see it's greatly increased along this extended defect. And really this is really showing a potential leakage path here in the device. So this is kind of very exciting, because oftentimes within the STEM data of this kind of issue, all you'll see is a single threading defect. You wouldn't really realize that the material around it has been affected so greatly, right? And so in structures like this, the doping is really important in terms of controlling the electronic properties of the devices. And this is obviously an electronic defect here. It could cause problems. So a little more examples of doping. This is silicon doping test structure that was created with a variety of different doping levels, layers 1 through 7. It's going from highly doped to lower doped as you go here towards the surface. And on the left here, we have the pan-chromatic CL signal with this sort of temperature lookup table applied to it, right? And so the darkest reds are the most intense. And then here we can actually then take that data, and looking at the main band edge peak, we can then look at the full width half max, and we can see the whole map of that as well. And then if we take these peaks and measure the full width half max of each layer, we can then plot that relative to the doping level. And so this structure was previously analyzed with SIMS to give us these doping levels, and we can see how the full width half max progresses with doping levels. So essentially our peaks broaden as the doping level increases. So this gives us a way now, once you have this type of text structure, you can utilize this as a control, and now you can then apply the same analysis to your unknown sample and have a better idea of what the quantified doping levels are within your structure. And then in the case of failure analysis, this is a case where we're looking at a new laser versus an H laser, and the processes that go on to degrade the sample. And in this study, they're figuring out that the degradation originates from a diffusion process, which then increases the threshold current. And nanoscale CL points out the circular symmetry of the degradation, which ends up being wider than the ridge itself by a bit, and includes the cladding layers as well. They noticed that the yellow band emission also decreases within this degraded region, whereas the intensity then increases outside as well. And then the wavelength fluctuations within both the quantum wells and the waveguides, which are determined to be that it's most likely due to an inhomogeneity in the indium concentrations with a possible effects on filamentation of the laser emission eventually. So here, just the power of being able to, analyze various emissive properties of lasers at different stages of reliability testing, for instance, to then basically back out specific degradation mechanisms. And then the last example we're going to talk about is looking at silicon doping, but now in a nanowire. And this is an example of silicon doping in gallium arsenide nanowires. And so in this finite structure here, it's about approximately 125 nanometers across, maybe 150 nanometers across. And then we can see while the SEM image is very consistent, the actual CL intensity from the nanowire is fairly inconsistent, which then gives rise to we can see that how the peak energy shifts within the structure, and then we can look at the full width half max again, and then utilizing similar calibration standards, they can then back out the doping concentrations within the nanowire itself. And here you can see the effective broadening that's occurring at different doping, and comparing the nanowire to their dope layers, etc. They can then make very good estimations of the doping concentration along the nanowire itself. So that takes us to our case study, which is the commercial blue InGaN high brightness LED. So the purpose of this study is really just to show how we can make targeted fib cross sections with low surface damage and implant specifically for CL exploration, and then also be able to do subsequent STEM analysis of the same location. So in this case, we've got a decapped LED dye that was harvested from a commercial light bulb purchased locally. We can then put down our protective strap in the focused ion beam and then create our cross section. In this case, we're actually lifting out the cross section and keeping it fairly thick to begin with, on the order of a couple microns thick. So bigger than the interaction volume of the SEM-CL that we're going to be doing, and ultimately only really polishing the one side that we're going to analyze. But here you can clearly see the structure of the LED. So we've got a patterned sapphire substrate, we've got some variety of GaN buffer layers, and at the very surface we have some AlGaN and then InGaN active layers. And then this is just a STEM HADF image to show that active layer region at the very surface. So we can see here we have, I think, 10 or 11 quantum wells, and then this is the AlGaN electron blocking layer up here. And so just to get an idea of the kind of data that we collect here, on the right, this is our hypermap, and we're actually, it's scrolling through, showing you, scrolling through and showing the wavelengths as we go. So the intensity, the emission at particular wavelengths. And so we then have access to be able to look at very specific wavelength emissions in the sample. So this is giving you an idea of the amount of data that we have here that we have access to. So ultimately, you know, we're having to try to make reports and boil this very, very complex data down into these two-dimensional images, etc. So here on the left, we take an SEM image of the area before, and then we take an SEM image while we're scanning, and you can see that the resolution of the CL scan is significantly lower than a typical SEM image. So the actual dwell times are on the order of milliseconds versus fractions of milliseconds for a typical SEM image, right? So to be able to take these images within a reasonable amount of time, we have to reduce the actual pixel density of the maps themselves. Ultimately, if we work, this is a case of working at room temperature. So if we worked at cryo temperatures, we would actually be able to increase the emission intensity by maybe 100 times more light will get out. So ultimately, there's some aspects of doing analysis at both room temperature and cryo conditions. And in some cases, if you're really interested in different defect states and things like that, you have to use cryo. But so if we can take our map itself, our panchromatic map here, which is showing all the wavelengths. So this is all the intensities over all the wavelengths summed together in one map. We can actually extract specific spectra from locations within the map, and you can see that here. So here at one in our sapphire itself, we get characteristic emission here down around 335 or so. And then we can see in the different GaN layers, we get a variety of different emissions. And then the multi-quantum well is up here around 440 is what we expect for a blue LED. And then we see some evidence of yellow emission here at points 3 and 4 in these specific GaN buffer layers. And so I guess one thing to note too, I didn't show down here, but effectively Like I mentioned, we have access to changing gradings. So here we're using a fairly low resolution grading, so 150 lines per millimeter. And then this gives us about 1 to 2 nanometer spectral resolution. And then in terms of the map, this is approximately 128 pixels tall. And so we've got about 200 nanometers per pixel spatial resolution in the map itself. And so we can then take a map of another region, take a second map, a little bit more zoomed in, because what I noticed before was that around 395 up here in the quantum wells, we start to get emission from very specific spots along the multi-quantum well. And so it's curious, now we can look at the overall spectral map again, and then we can apply these notch filters like we did before at certain points where C here is the this 391, 395 emission. You can see that we get a little bit of emission at different sites, primarily at these two locations here. And then we can also, visualize very quickly the different materials that are present in the sample, and or the variety of different aspects of the luminescence in the growth, right? So this first GAN buffer layer has some very interesting geometries to it. And then we see this elevated, increased emission in these second and third layers as well. So for some reason, there's the emission in these layers is being suppressed for some reason. Similarly up here. And so from this kind of situation, we can then take even higher resolution maps. So this is a third map now up at the very surface. We can apply these different bands again, and then we can actually take this kind of map and then overlay it on our SEM image. And in fact, what you can see here in the SEM signal is evidence of a V defect, similar to the one I showed you before in that doping metrology example. But in this case, it's outlined well by the electron blocking layer that we're seeing here. And then this brighter layer here is the multi-quantum wells. And so we can then see that this 396, this blue shifted emission, is actually occurring right at the base of this V defect, right? And then some of the other things that we can see is that there's sort of uneven emission. So this 440 emission for the multi-quantum well region actually is composed of several emissions, and it looks like it red shifts slightly as you travel up the quantum wells. So ultimately, it looks like the most intense 440, 436 emission is here towards the lower portion of the quantum wells, and then you get lower intensity emission at larger wavelengths as you move up in the epitaxy. And then, just for example, here we've changed to a different grading. It's important to note. So here now we're only collecting about 125 nanometer range. So we've got about 0.15 nanometer spectral resolution now. So we can really discern these subtle differences in the emission properties around this specific site. And in this case, we're collecting a similar pixel density, but we're zoomed in quite a bit. So now we're looking at about 125 nanometers per pixel resolution in terms of the SEM itself, and then the CL data as well. And so here once again, we can extract specific spectra from the CL map itself. And so we can compare, for instance, 3 being in the V defect, that bright spot region, versus sort of what we would consider normal multi-quantum well in number 5. So number 5 is this pink emission here, very close to 440, which is expected. And then 3 here, this is coming from the V defect. So we see this highly blue shifted region within the spectrum of this particular area. And so other ways we can try to visualize this as well, we can actually take line scans through the spectral map and then plot that. This is called stripes view. So we can plot each of these spectra as sort of an intensity map here. And along this particular line, there's 53 extracted spectra, and then the wavelengths are here on the bottom from left to right. So you can see primarily in the good region of multi-quantum well on either side of the V defect, we're getting high intensity of emission around 440, 439. But as we go into the V defect itself, the emission intensity lowers, but also blue shifts greatly, right? So now we're getting primary intensity around 400 nanometers, 396 or so. So this is just another way we can look at features within our sample and try to understand how the emission is changing relative to the sample itself. And then we can also do things like extract line profiles from mono CL data. So here we've extracted 3 different maps at each of these different wavelengths, right? And here the 396, this is about a 27 nanometer notch filter, or looking at this specific emission at the base of the V defect. And then we have 436 and then 459, which is further redshifted. And then we can correlate this to the SEM, the SEM signal, the SE signal intensity, right? So we can then overlay all of these, and then you can sort of see where the maximum of these emissions are occurring relative to the multi-quantum well. So you can see that this blue shifted 396 emission is actually deeper in the sample than either of the 436 or 459. And then you can see this tail of 459, how it proceeds towards the surface as well. So all this kind of information may be very important or valuable to the people that are designing the structure, and it's more than likely correlated with the material properties, which I haven't been able to do further analysis of yet. But for instance, it seems like maybe it's related to the quantum well indium concentration, for instance. Maybe the indium is increasing through each quantum well, or something of that nature. And so here we can also then do things by correlating data. In this case, we've made a STEM cross section of this exact location that we did the SEM-CL of. So we can then correlate the SEM-CL overlay that we did previously within the STEM data, and you can get an idea of where exactly the emission is occurring. And so you can really now see there's a variety of crystal defects. There's threading dislocations that come through here. There's multiple dislocations that are created in this region. This is actually a fairly complex structure. It's not just a single V defect, but it's actually probably an interaction of several together. And so in this region here, we have the sidewalls of the V defect. There's actually very, very thin multi-quantum wells that go down the sidewalls. So it's quite possible that this emission is related to that. So maybe it's related to the non-polar multi-quantum wells here, grown on the non-polar facets of the V defect, of something of that nature. It is very surprising, however, that we have these threading dislocations, and it doesn't really seem to be decreasing the intensity of the CL emission very much. So that's one curiosity, and that sort of gives rise back to the ideas of convolution of information. So when you're doing SEM-CL, for instance, you've got this larger interaction volume, and you're detecting potentially things that are smaller than that interaction volume. And so maybe we're actually looking at a lot of good material here, as well as the material that has the defects in it. But overall, it's very, very interesting. And ultimately, what we'd really like to be able to do is be able to take CL from this specific STEM sample itself. And so we're working towards that here in the lab, acquiring SEM-CL capability. And so the last thing I wanted to finish on was really to drive home the idea that spectral interpretation ends up being really the trickiest part of all of this, and can be very, very time consuming. This is a paper, pretty well known paper from 2005, that lists a lot of the luminescence properties of different defects in GAN, as they were known at the time. There was a lot of CL and PL comprised within this. And this list is obviously non-exhaustive, and this is from 2005, but there's already very, very many different attributed CL emissions from a variety of different known defects. So there's a lot of unknowns still, and a lot of work being done currently. But that's the beauty of it, is that really, I think people are really starting to realize the power of the technique. So you're getting a lot more publishing of CL related data in the literature. So really, how do we determine what is what going on in our spectra? So we're going to utilize the literature as much as we can. We're also going to try to set up comparative analysis between samples, for instance. So can we create specific signatures that are important to us that can help us understand other and relate to other positive attributes to devices or material, et cetera. We're going to create and use standards whenever we can. And then we're also going to utilize complementary techniques for clarifying things. So things like doing photoluminescence or scanning microwave impedance microscopy, which is an AFM technique, doing Hall effect measurements on our control samples and SIMs as well on control type samples. And then obviously doing things like TEM or STEM of samples as well really helps provide the overall picture. So in summary, SEM Cathodoluminescence, or SEM-CL, is a great choice if you need to understand the physical and optical properties of your sample with very high spatial resolutions on the order of tens of nanometers. It's important to remember that we can actually detect atomic scale defects with this technique. It gives us access to a wealth of information of both majority, like alloy compositions, et cetera, and as well as minority constituents like doping or point defects, et cetera. It's both qualitative as well as can be quantitative with the right situation with controls, et cetera. And data acquisition is fairly straightforward, but sample prep and data analysis is often non-trivial. And so it is really important to understand potential effects from various sample preparation techniques such as FIB, but oftentimes there's really no way around it because we really need to study this very specific spot on a sample. So it's important to gain that knowledge of how to make samples as uninvasively as possible. And so ultimately we're open and welcome to collaborative relationships with our customers regarding larger projects, especially if they're interested in doing the data analysis themselves as well. So we're glad to take the data and follow your lead, and you guys can, essentially keep the IP to yourself as well. Currently, we're working towards adding SEM-CL capability in the near future so we can really improve the spatial resolutions we're capable of, and that'll give us about an order of magnitude better over SEM-CL. So get down to sub 10 nanometer resolutions. And so with that, I'd like to just say why choose Eurofins EAG Labs. So client confidentiality is core to our business, and we're established thought leaders in investigative science. We have extensive knowledge base and skilled expertise to help you. We can offer a multidisciplinary approach to support any of your major projects. We can then scale with your demand and also meet your various time constraints. We own more than 2,500 instruments worldwide, and we are a global leader for material science testing services, also ISO 9001 and 17025 quality accreditations as well. So we can help solve your materials and engineering related problems. And with that, I'd like to say thank you.